Experimental theoretical probabilities. In your notes packet, what you see right now is a table. We're on Learning Target 10.2, and this table describes the everyday language and then how do we find it. With this, you're going to find that in the theoretical and experimental boxes, these two things need to be switched. It's typographical. They're not correct where they're at. So you need to switch all those, and yes, I see there's a typo right there as well. It's outcomes, but we won't worry about that. But overall, theoretical and experimental probability. Theoretical, what we think is going to happen. Not actually what is happening, but what we think is going to happen. P of E means the probability of an event, probability of an experiment, probability of a likely outcome, whatever we want to have. So the probability of a head, probability of getting a 3 on a coin, whatever it might be, that's the probability. That's what that P of E stands for. P stands for probability. E is what event is occurring. What do we want to happen? And then that's equal to the number of successes divided by the number of trials. Experimental probability based on actually what happened during an experiment. We flip a coin 100 times. What was the probability of a head? How many heads do we get? How many tails do we get? That's experimental probability. It's the number of times the event occurred out of the total number of trials. So those should be switched around. And then geometric probability is using lengths or areas to find it. So we find, like on a dartboard, what's the probability of getting a bullseye? So you'd find the area of that bullseye and then divide that by the total area of the dartboard. So we can do it but with areas as well. In other words, the probability, what the number we want, the number of likely outcomes, or the number of successes divided by the total number of possible outcomes. It's successes divided by the sample space. How many possible outcomes are there? So we'll do some examples. Find the theoretical probability assuming you roll a pair of standard number cubes or standard dice. What's the probability of a sum of 6? So we're talking about the sum of 6. So what I've done down here at the bottom is I have identified the sums of rolling 2 dice. So here is die 1, die number 1, and on this side is die number 2. And what happens when I roll a 1 and a 1? I get a sum of 2 and so on. So this table fills in all of that. Here, what we want is we want the probability of a sum of 6. So in the black circles, I have identified the ones that add up to be 6. There are 5 of them. Okay, and this is not an experiment. This is theoretically what we think is going to happen. There are 5 out of how many possible outcomes are there in this table? Well, 6 times 6 is 36, so there are 36 possible outcomes, total possible outcomes. Okay, so that's the probability of the sum of a 6. And typically, we're going to write them. You don't need to, once you get them in a fraction, you can just leave them that way. Yeah, we want to try to reduce the fractions, but you don't need to actually divide them out and get decimals or change. We definitely don't want to change them to percents. Part B, the sum less than 5. So I've highlighted the ones that are less than 5 with a yellow highlighter. How many are there? You'll notice that there are 6 of them that have a sum of less than 5. So that's 6 out of 36, and we should reduce that down to 1/6. So the probability of getting a sum less than 5, that means the 2 3s and the 4s, less than 5, so it does not include the 5s. All right, next one says, Callie rolled a pair of dice 300 times. She got a sum of 6 48 times. What is the experimental probability of rolling a sum of 6? Well, this is experimental. She actually did the experiment. So it's out of 300 times she rolled it. How many times did she get a probability of a sum of 6? 48 out of 300. Let's divide that by, let's reduce that down so we can divide them both by 6. That's going to leave me 36, 42, 6, 8. Out of 50, I can reduce that a little bit further. That's 4 out of 25. So 4 out of every 25 she got a sum of 6. All right, continuing. Here we have some more examples. If you choose one card at random from a deck of 52 standard playing cards, what is the probability that a card you choose is a heart? So again, we're thinking about theoretical probability. The probability of getting a heart. Well, there are 13 hearts in a standard deck out of 52, or 1/4. Okay. And then second part, what does a standard deck of playing cards look like? There's 4 suits. There's hearts, diamonds, clubs, and that's a horrible club. And then there's spades. And then in each suit there are 13 cards. And those would be ace, king, 10, queen, or ace, king, queen, jack, 10, 9, 8, 7, 6, 5, 4, 3, 2. All right, if a circle is with a radius of 10 is placed inside a square with a length of 20, like the drawing. So we have a circle that has a radius of 10, but the length of the side of the square is 20, and that would make sense because it's inscribed inside the circle. What is the probability that a dart thrown will land inside the circle? So we have to find the probability of it being in the circle. That's the area of the circle divided by the area of the square. So the area of the circle, if you remember, area of a circle is pi r squared. Area of a square is the side squared. So in this case, pi times 10 squared over 20 squared. And we can continue. That is 100 times pi over 400, which is about 314 divided by 400. And we could change that to a decimal if we like. And in doing so, we wind up with 314 divided by 400, 0.785. So the probability that if I throw a dart at random at this circle, or something's going to land inside this circle, it's going to be 0.785 is the probability. Okay, so what's the probability it's going to land outside the circle? It would just be 1 minus that, the probability outside the circle, but still inside the square. All right, going on. The following table shows a random sample of 100 hikers in the areas of hiking preferred. So it lists some items. We know there's a total of 100, so we need to be able to fill in the table as well based on what they give us. So we know there's a total of 100 hikers, so we can fill in that one. What else can I fill in? Well, I should be able to fill in, because I have 18 and 16. I should be able to fill in like hiking on Mountain Peak, because the total is 45. 18 and 16 is 34. 45 minus 34 is 11, so I can fill in that one. Next, well, that means I can fill in this one, because 11 and 14 is 25. If I know that there are 16 females that like to hike near lakes and streams, and there's 41 total, I can fill that in. That's also going to be 25. And if I know those two, and that's a total of 55, in those two rows, or I can do it a lot of different ways. But 55 in those two rows, if I take away 25 and 14, that's 39. That leaves 16 to go here, and that means 34 there. And those should all add up to be 100. So now, being able to fill in that area, or fill in a table given some information, you should be able to do that. Determine the following probabilities. Probability a female likes to hike on the coastline. So we have to look at only the females that like to hike on a coastline is 18 out of total 100. And then we will reduce that to 9 out of 50. Next one, probability a person likes to hike on mountain peaks. It doesn't say male or female, so total number of people who like to hike on mountain peaks is 25 out of a total of 100, or 1/4. Next one, probability of a male likes to hike near lakes and streams or on the coastline. So near lakes and streams is 25. And we're looking only at the males, 25. And on the coastline is 16. So that adds up to be 41. So this one's going to be 41 out of 100. Okay, or 0.41. And that's all for our video for today. Come to class, we will be doing some more exercises with these examples, or following these examples.